Hello everybody, we're getting ready to do section 17 of SAT Math Level 2 preparation. And for 17 is complex numbers. You got 10 points in your notebook guide, have that out. We go through powers of I, arithmetic of complex numbers, and graphing complex numbers. And you have 6 points on your classwork sheet. Name, date, period, students in my class, due date for onliners and homeschoolers, put your due date here. And we go right into slide number 1, page 1. The square of a real number is never negative. This means that the square root of a negative number cannot be a real number. The symbol I equals the radical negative 1 is called the imaginary unit. I squared equals negative 1, so this I squared would equal negative 1, and then this would be the square root. The square root of negative 1 would equal I. You take radical negative 1, radical I squared, and you get I equals negative 1. Powers of I follow a pattern. So here is a table. So we have I to the first equals I squared equals negative 1, I cubed equals negative I to the fourth equals 1, I to the fifth equals I. So we go I negative 1, negative I, and then back to I again. So we have like a 4-step process here. To get back to here, it takes increments here of a power to get back to I. In other words, the power of I follow a cycle of 4. This means that I to the nth equals I to the nth mod 4, where n mod 4, the remainder, when n is divided by 4. For example, I to the 58th will equal I squared equals negative 1. So basically you can reduce this as an even number, so it'll be a square. And then because it's 29, it's 2 times 29 will equal 58. So it can be reduced to an I squared, which is negative 1. So I to the 58th power will be negative 1. The imaginary numbers are numbers of the form bi, where b is a real number. The square root of any negative number is I times square root of the positive of that number. Thus, for example, square root of negative 9 equals I times square root of 9, which will equal 3I. Now the square root of negative 12 will equal I times radical 12 will equal 2 times I to the third, or rather radical 3. And then the radical negative 7 will equal I to radical 7. Complex numbers are formed by attaching imaginary numbers to real numbers using a plus sign here. The standard form of a complex number is a plus bi, where a and b are real. The number a is called the real part of the complex number, and the b number is called the imaginary part. If b equals 0, then the complex number is just a real number. If b does not equal 0, the complex number is called imaginary. If a equals 0, bi is called a pure imaginary number. Examples of imaginary numbers are 2 plus 3i, negative 3 fifths plus 4i, 6i, 0.11 plus negative 0.45i, and pi minus I times radical 5. These are all called imaginary numbers. When the imaginary part of a complex number is a radical, write the I to the left in order to avoid ambiguity about whether I is under the radical. Finding sums, differences, products, quotients, and reciprocals of complex numbers can be accomplished directly on your calculator The imaginary unit I is the second decimal point on the graphing calculator. If you enter an expression with I in it, the calculator will do imaginary arithmetic in real mode. If the expression entered does not include I, but the output is imaginary, the calculator will give you the error message, non-real answer. For example, if you tried to calculate the square root of -3 in real mode, you would get this error message. In A plus BI mode, however, the square root of -3 would calculate as 1.732i. You should use A plus BI mode exclusively for the level 2 mathematics subject test. Although complex number arithmetic per se is not likely to be on the level 2. Mathematics subject test. Understanding how it is done may be. So you may have to understand it, but the actual calculating it probably won't be. A review of the main features of complex number arithmetic is provided in the next several paragraphs. So to add or subtract complex numbers, add or subtract the real and okay, so we're going to get into evaluating an imaginary number here. We got 5i minus 7i plus 2 plus 4i. So here is our sum here, and this comes out to being 7 minus 3i, 5 plus 2, and then negative 7i plus 4i give us negative 3i here. Now, to multiply complex numbers, multiply like you would any two binomial expressions using FOIL. Thus, a plus bi multiplied by c plus di will equal ac plus ADI plus BDI squared plus BDI squared plus BCI. So BCI here first. BCI, then BDI squared. Now I squared is -1, right? So this becomes negative. BD becomes negative. Then we have AC. And then we have AD plus BC multiplied by I. So here will be your imaginaries over here within this parentheses here. So that will be how you would get this sum from that. Evaluate 4 plus 5i multiplied by 2 minus 3i. So 4 plus 5i multiplied by 2 minus 3i will equal 8 plus 10i minus 12i minus 15i squared will equal, then when we combine similar numbers, it will be 8 minus 2i, so 8 minus 2i plus 15 will equal 23 minus 2i from that. So minus 15i squared, 8 minus 2i, this will be 2i, then 15i here. The difference of the first and last terms makes the real part, and the sum of the outer and inner terms make the imaginary part. Now, so 15i squared here, this will become -1 times 15, will be a positive 15. Plus 8 will be 23. So this goes away. It becomes a real number then. So evaluate 2 minus 7i over 3 plus 5i. So to find the quotient of two complex numbers, multiply the denominator and the numerator by the conjugate of the denominator. So multiply this by its conjugate. Then simplify. So 2 minus 7i, 3 plus 5i will equal 2 minus 7i, 3 plus 5i times, what's the conjugate of 3 plus 5i? It'll be 3 minus 5i, and then 3 minus 5i. When we do that, we multiply these together here. We get negative 29 minus 31i, and then this becomes 9 plus 25 here, which is 34 over, rather 29 over 34 here, minus 31i over 34. So that would be how that would be multiplied across. A complex number can be represented graphically as rectangular coordinates, with the x-coordinate as the real part and the y-coordinate as the imaginary part. The modulus of a complex number is its distance to the origin. The Pythagorean theorem tells us that this distance is the radical a squared plus b squared. The conjugate of the imaginary number a plus bi is a minus bi. So the graphs of conjugates are reflections about the y-axis. Also, the product of an imaginary number and its conjugate is the square of the modulus, because a plus bi times a minus bi equals a squared minus b squared I squared, which will equal a squared plus b squared. So that's how you get that. Again, if you need more background on imaginary numbers, I have packets for that as well. Contact me here at Animated PowerPoint Math Video at AOL.com for questions or course materials. Thank you very much.